chord. All right, so if n has exactly 7 positive divisors, how many positive, no e, just it's a very edgy positive divisors does n squared have? Take a minute and think about this one and what that would mean for us. What did we get for this problem? Ananya.
If it has exactly 7 positive divisors, you know, it's n has an exponent of 6. And then once you square that, you get n to the 12th, and then you add 1 to 12 and you get 13.
And that gives us 13, which maybe I can drag and move. Yeah. Is there any way we could have broken it up so it wasn't like, could we have done this maybe as 2 possible factors? So like a, you know, squared and b to something, would that have worked or not?
It wouldn't, because 7 is prime.
Yeah, 7's odd. So what does it mean? What does n have to be here?
A perfect square.
A perfect square? N has to be a perfect square. What if this were, like, let's say, for example, 6 squared is really 2 to the 4, no, sorry, not 2 to the 4th. That's 2 squared and 3 squared. And so isn't 36, like 36 is a perfect square. How many divisors does this one have? It's got 9. What's up with 7? What's the problem with 7? Because we know odd divisors totally have to be perfect squares. Why is 7, like, why can't I make 7 in some fashion like this? Like, what if I were to do like 18 squared? That would be like 2 squared times 3 to the 4th, which gets me 15. It's prime. Why does that matter, Ashmita?
Because you couldn't break it up. Like you can break 6 into 2 squared and 3 squared, but you would only be able to do 7, like 7 times 1.
Yeah, we can only do 7 times 1. So the powers have to get some, it has to be like 6, like n to the 6, and then times nothing else, right? There's no way we could make 7 as a product of 2 other ones unless the one was a product of 1. It's still not graded. Okay, I will do that. Sure. Yeah, that's fine. If n is a perfect cube, it's a perfect cube of a natural number, and n has 28 positive divisors, 2 of which are prime, how many positive divisors does the cube root of n have? Ho, ho, ho. Let's take a minute on this one. What did we get? Someone walk me through.
Since you know that n is a perfect cube, the exponents have to be multiples of 3.
So the exponents, so like let's say a, b, c, they have exponents x, y, z. Let's do that. That seems nicer. X, y, z. You know x is divisible by 3, y is divisible by 3, and z is divisible by 3. Okay. Now what?
And since 28 is broken up to 4 and 7, so you could have the exponents 3 and 6.
4 and 7, so that's 3 and 6.
And then it's saying 2 are prime, so that means that you have 2 prime factors, that like a and b.
So a and b are prime. Okay.
I just put the smallest ones, so like 2 cubed and 3 to 6.
Yeah, so we pick some prime, right? We don't necessarily carry which ones.
Oh, yeah.
Yeah. Could there have been another factor? Ooh. Crickets. We don't think that there's another factor, is what I'm hearing. Nah? Why not? If no, or maybe you're uncertain, why do we give me an argument of why you think there could be or couldn't be? Ishin?
Well, I have a question.
Sure.
How did you get the 3 and 6?
So we got the 3 and 6 because we know that if like x is the exponent, then x plus 1 is the amount of divisors it would have. And so if we have like 4 and 7, that means that the powers would be 3 and 4, or 3 and 6, because that's how we figure out how many divisors there would be.
So technically you could still have like 2 and 14, and then it would be 3 and 15.
So if it were 2 and 14, then that would bring down to 1 and 13. You gotta go down. And there's a reason, why don't 1 and 13 work? What's the issue with 1 and 13? Because that's a good question, right? We want to talk about why 1 and 13 is, which is the other version of this, is not acceptable.
They're not divisible by 3.
Yeah, these numbers have to be divisible by 3. And so 1 and 13 don't work. 3 and 6 are okay, 1 and 13 are not. Okay, so we're down to 3 and 6. How many possible divisors does the cube root have? And so if you were to take a cube root, we're getting 1 and 2. And so that makes it, we add 1, that gives us 2 times 3, so a total of 6 divisors. We have still not addressed the fact that could there have been another factor? Also, let's talk about the fact that this 2 and 3 are arbitrary, right? These two, this 2 and this 3, that's just random primes, right? You could have made it 11 and 13 if you wanted. They just have to be prime numbers. Could have been 7 and 5. We don't care. Can C exist as an integer greater than 1? Why or why not? All right, take a second and think about it. Olivia, what do you think?
Oh, wait. Oh, never mind.
Okay. Yeah, C has to be a prime. Let's start with that. C has to be a prime for our prime factorization. So could that work? Yes or no? It says 2 of which are prime. It does not say that there are only 2 divisors, though. Does that make sense? It's not saying that there's only 2 factors. It just says that 2 of which 2 are prime. Yeah, I guess it did just say 2 of which are prime, so maybe that's saying only 2. I guess we can go with that argument that only 2 would be prime. What I'm trying to play at is what say we didn't have that. Say there was like another factor in here. Say like we had 2, 3, and 5, all 3 primes. What's the problem with that? Where our powers have to be then?
1, 1, and 6.
Yeah, we'd have to break it down into 2, 7, and 2, which is 1, 6, and 1. And then what's the issue with 1, 6, and 1? Or 1, 1, and 6, however you want to do it. What's the problem with that?
It
They're not
doesn't.
multiples of 3.
Yeah, they need to be multiples of 3, right? It's got to be a perfect cube, so can't be that one either. Cool. All right, let's keep this train moving. If I can move the box over, there we go. Okay. So how many positive divisors of 960 have 6 positive divisors? How many positive divisors of 960 have 6 positive divisors? Take a second and think about this one. All right, what did we get? What do we think? What are we feeling?
You to first find the prime factorization of
Yeah.
960.
What's the prime factorization of 960?
2 to the 6 times 3 times 5.
Are we cool with that? Does anyone object? Yes, we're okay with that. Okay, so now how do you figure out which ones have 6 factors?
Well, you could split up 6 either into something with the exponent of 5 or something with the exponent of 1 times with the exponent of 2.
So we could have just straight 2 to the 5th, right? Or we could have it as 2 to the what? Second?
Yeah, and to the first.
And 3 to the first, or 2 to the second, and 5 to the first. And either way, that'll get us 6. Nice, nice, nice. So we only have these 3 as our options. Not too shabby, gang. Not too shabby. All right, well, second to last one. We got 2 left. If M has 10 positive divide, man, am I incapable of spelling? I cannot spell to save my life. You would think the red squiggle. Oh, now let's just put a 0 in there. All right, there we go. Has 10 positive divisors and has 6 positive divisors. And the greatest common divisor of M and N is 1. How many positive divisors does M times N have? What do we think? I feel like we could probably shoot this one off the cuff. I don't even think we need to pause. I think we just big brain this and figure it out. Olivia, what do you think?
Do you just multiply them together? Because
Why?
they're relatively prime.
Yeah, they're relatively prime. So that means if they have like A to the whatever and B to the whatever, then we realize that because they're relatively prime, they don't share any factors, that we would just be able to take the product of the amount of divisors they have. But this only works if they're relatively prime, right? So if they weren't relatively prime, then we don't really have any way of knowing, because like, let's say, like, let's think of 2 things that would have 10 divisors. We need a 5, so 3 to the 4th, and then 5 to the 1st, right? This would have 10 divisors. And then the other one could just be either like 3 to the 5th or 5 to the 5th, or we could have it as some kind of like 2 and a 3. We could have 3 squared times 5 to the 1st. All of these things would work. And if we multiplied these together, we'd end up with still 10 divisors. So because they're relatively prime, we can just take the product of them. Can I explain that one more time? I would love to. So they're relatively prime, which means that none of their factors are going to overlap. So like if this had factors, prime factorization, for example, of 3 and 5, this is not allowed to have 3 and 5 with it. It has to be some other distinct prime. So let's just say this is A to the 4th, B to the 1st, right? Because that's how we could have 10. Or it could just be A to the 9th. Either way, but those are the 2 ways. Or I guess we could, no, that's the only 2 ways. The other way we could do this is the other number has 6 possible divisors, but these are all relatively prime. So A and B are not factors of this new number N. So this could have 5, or it could be like C and D, and one's like 2 and one's 1. Those would be possibilities. But regardless, whenever we multiply these things together, we end up with the exact same thing, right? They still have the same amount of divisors with their product because of their relatively primeness. Does that make kind of sense? I'll take that as a yes. That makes kind of sense. Okay. All right, last one. I saved the best for last. Hold on, let me make sure. Okay. Best for last. Oh boy. So this is you trying to derive this. So I want you to start by listing the positive divisors of 60. Don't just give me the prime factorization. Give me the actual positive divisors. And then beneath each divisor in your list, write the quotient of 60 divided by the divisor. And then find the product of all positive divisors of 60. So now we're finding the product of all the positive divisors, which is wild. And then you're gonna find a formula for it. So take a couple minutes, try this one out. All right, so what are our factors of 100, or sorry, our factors of 60? We got 1, 2, 3, 4, 5, 6, 10. What am I missing? 15, big old 20. Oh man, I forgot 12. I'm so sorry. Would have ruined everything if I just forgot 12. 12, 15, 20, 30, 60. Okay, we're fine now. Now this is similar to what happens if we were to do this via adding, but we're gonna do it with multiplication instead. So we're gonna do essentially the reverse order underneath. 15, 12, 10, 6, 5, 4, 3, 2, 1. What do you notice?
The second one just written backwards. The division.
Raksha, what were you saying?
I did a different thing. It's for the product, not that.
Oh, okay. What do you get for the product?
So when I multiplied all of them out, I realized there's a pattern with the power of the original number.
Yeah.
And when I multiplied all the factors out, I got a big number. I got like 70 million. Wait, no, 777,600,000. And I realized that it's probably going to be a power of something. So I square rooted it, and I got that to the power of I got 60 to the power of 5 equals that big number.
What?
And then I realized that there's 10 factors. So I was thinking maybe it's the power of the factors divided by 2. And then I checked it on another number and it worked.
So the power of the factors divided by 2. So what do you mean by that?
So like it has 10 factors,
Mhm.
and then the power is 5. So you have to divide the amount of factors by 2, and that's going to be what it's raised to.
So let's say it's n, and then the number of factors it has is like t of n. So t of n is the number of factors. Number of factors. And then divided by 2. How does this work? Why does that make sense? Because I 100% agree. So do a lot of people in here. Ishin, what do you think?
Isn't it that squared? Because he said he square rooted it to get the 60 to the 5th power, I think, if I heard it correctly.
What do you mean? Oh, he square rooted this?
Yeah, if I heard it correctly.
Why did he square root it?
I don't know, that's just what I heard.
Oh, okay, fair enough. Someone said, isn't it 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, there are 12 factors. So shouldn't that be to the 6? Isn't that 12? Right? Am I right or am I wrong? I could be wrong. Come on, people, work with me. Why are we throwing in the chat? Why can't we say with our mouths? Oh, you got 4. Okay, Prakshaw, I apologize, but it should be a bigger number, even larger number than what you got.
Yeah, it's 4 to the E. I just realized something like calculator.
Worries. Well, you probably went with the 10, and so that made sense. So it should be 4, 6, 6, 5, 6, and then just so many zeros. 6 zeros. My goodness. And then you took the square root of that, and then that got you 60 to the 6. Why are we taking the square root though? Why even take the square root? Hold on, let me throw Ishin. Or is yours from before?
Mine was from, I think that's wrong. You
Oh,
don't
okay.
have to take the square root.
Don't have to take the square root. Okay, so you're saying that this is 60 to the 6 without the square root. And Anya,
Well, the number without the square root is like the product 1 through 60 is if you multiply every single number in
Yeah.
like the two rows,
yeah,
that's just 60. That's just the product of the first row squared.
yeah. So this is, let's look at this. These multiply together. So maybe we get back to this. This is 60. Each one of these multiplies together to get 60. So we essentially get 60 12 times. But we can't just multiply by it twice, right? That's not allowed. So we take the square root of that, and that gets us 60 to the 6. So I think Prakshall's original idea, while it may have been founded on the incorrect number of factors that he thought, it still works. That's still a thing. If we take our number and raise it to the number of factors divided by 2, that will still get us the same number, right? That's what we're hoping for. This will tell us the product of all of these, no matter what we're dealing with. So yeah, I think that's the formula we want to look for. So if I were to say, hey, what's the product of all the divisors of 210? You could just say, okay, well, 210 is 2 times 3 times 5 times 7. So that's 8. So the product of all of them would be 210 to the 4th. And that would be it. Which then if you wanted to know like how many factors it would be, like if you want to be like, oh, how many factors would all the factors be? Then you could just do 2 to the 4th, 3 to the 4th, 5 to the 4th, 7 to the 4th. And so that's like 625, which is wild. All right, questions, comments, concerns? Cool, cool, cool.